Hello everyone, welcome to another video from the AI Loop. Today we're going to be talking about masked multi-headed attention. So let's start. So before we start, I just want to say that when we have a decoder block, masked multi-headed attention is the first block, like the first block of attention that you encounter as soon as you enter the decoder block. So this is what we're going to be talking about today. So before I start with the concept, let's talk about how the transformer actually decodes. So when you give the transformer a task of predicting a particular sentence, and let's say the sentence is what is it, or like a sentence like how are you, how is it actually going to predict? Let me just write the sentence here. Yeah, so when we have this sentence, the way the transformer predicts is that we first, for the decoder block, it first predicts the word how, and then we give how as an input. It goes on to predict the word are, and then we give the words how are as an input to the decoder, which will then prompt it to predict the word you. And this is the way it predicts. So at a certain word, it's only able to see the words before it, right? Like when you consider the word R is only predicted from the information that we get from the word how, because this U is in the future and our transformer hasn't predicted it, so you would not be able to see it to gain any information. And let's talk about two things. Like after keeping this in mind, let's talk about two things. So we have two stages, right? For any model, we have the training stage where we train the transformer to learn, and we have the inference stage, right? So the inference stage is where we usually have the predictions done. So the case is that in the training stage we have the x to y mappings, whereas we know the input and we know the output, and we train the transformer to predict from x to y. And at the inference stage, we only have the input, right? And we don't know what the output is. It's supposed to predict y, but like we don't know what it's going to predict. So basically, masked self-attention is used to address this part. So how it works is that, or the basic intuition behind masked self-attention is that generally when we talk about attention, and let me write the sentence here again, and let's say this is our y, like this is the output. At this point we know what the output is. So but generally how it works is that in attention itself, the main factor or the benefit that the attention is bringing to the representation is that if you do not pass this, like before passing this word, basically we have a vector representation for everything, right? So before passing it to the attention layer, you have a vector representation, a learned embedding and a positional embedding. But these do not convey the information about the word in this particular sentence. It's a generalized representation and also the position that's encoded. But after passing it through the transformer, through the attention layer, the benefit or what we get from that is that the vector now, like the resulting vector after passing it through the attention layer, consists of this word's position or context in the whole sentence. So we will like get to know of information about how this word is related to other words in the sentence, and where is it positioned, and how much value is it adding to like the words before it and the words after it, and all that kind of information. So this representation is very sentence intensive, and it's a very good representation of that particular word in that sentence. So this is, and the way that this works is that for every word that you want to calculate a representation for, you draw in influence of all other words on it, right? Both from the left, like both from the words after it and both from the words before it. And what really happens in the inference stage, if you did actually focus on this part, is that when we're like at this stage of predicting is, we will not have an idea of the words coming after it, as in we would not have a clue about what this word is going to be or what it's going to be predicted as. So we cannot really draw any information from that word, because this representation of is cannot have any influence of words coming after it, because that does not make sense. You cannot see into the future. So this is basically addressed by the masked multi-headed attention. So in the attention layer, how it works is that, let's say for each of the, let me draw these, right? And let's say for each of these words, and let's suppose we have, and okay, let me just draw the query key and value vectors. So when we have the final input embedding, what we do is project each of the vector into queries, keys, and values, right? And basically the process is that we multiply every key with the corresponding query, and then scale it by the dimension of the embedding and do a softmax over it, get a probability and multiply each of the probability with the corresponding value vectors and add them up. So that's it. Basically, like we get like some percent, we take some percent of information from this and some percent of information from this and like some percent of information from this, and all the three things add up to 100%. So the way that masked self-attention works is that if you want to calculate the vector representation or the attention layer representation for the word is, we take the query value for this, we do the dot product with these two key values, and you will also do the dot product with this key value. This is in the training stage, guys. Like in the inference stage, we would not be having this part because it's not predicted yet. And what really happens is that we do these three multiplications, and then we divide it by the dimension of the embedding, and then we run a softmax, right? So this part, before running the softmax, for this particular combination of Q2 and K3, let's say the index starts from 1, we would set this to a large negative number. That, like, let's just write it as minus infinity, but you would ideally be setting it to a large negative number. And the property of softmax is that vectors that you give into it add up to 1, right? It gives you, so the higher the vector, the higher the probability. So the higher the number, the higher the probability. That's how softmax works. So when you like have three words, three scalars, and let's say for this you got 25, and let's say for the second one you got 55, and you're setting this to like minus 1000, let me just write it as 1k, I don't have space. So if you're setting this to as a large negative number, what happens is it returns probabilities such as 0.3 and 0.69, and I'm writing it as 0.01, but it would be a very it would be like even less, but it would be like way closer to 0. That means it's actually like a 0. So, and when you multiply them with their corresponding value vectors, what happens is that for calculating the representation for the word is, you take 70%, like 69% from the word is itself, 30% from this, and 0.01, or imagine a number that's like way below, but all of these should be adding up to 1, so I just wrote it as 0.01. So you would be ending up with like, let's say 1% of this. Ideally it should be a 0, so like, yeah, so you would be ending up with, so you would get all of your representations from this word itself or the word previous to it, and you would not derive any influence of the words after it. This way it ensures that it stays in check with the reality, and like that's the way the decoding also works. So at the decoding stage, you just have the previous words and you have to predict the next word, and the word representation only consists of the information from the previous words. So that is it for the masked self-attention. We just talked about it in terms of one head here, but remember that multi-headed attention happens here too. And that's it regarding masked multi-headed attention. Please subscribe to the AI loop. I'll see you in the next video.